Hello. Today, as a continuation of the topic chemical reactions and equations, we will introduce another one of the essential elements of working with chemical reactions and equations, the concept of the aggregate state of the reacting and resulting substances. Well, let's remind ourselves what these aggregate states can be. First of all, substances can turn out to be solid. For instance, let's say iron is in a solid state. In the reaction equation, they write the symbol for iron, and in parentheses, they indicate that iron is specifically in a solid form. And they write the first letter of this word, tverdi. Go ahead. Substances can participate in liquid form. The most familiar liquid substance is undoubtedly water. Water frequently reacts as a liquid and also assumes the form of a liquid during the course of the reaction process. Next up is gas. As an illustration, oxygen is classified as a gas. Subsequently, the formula of this substance will be documented and enclosed in brackets, once again, the initial letter of the term gas. Well, and water solutions can also take part. These are solutions that are typically dissolved naturally in water, since we are dealing with such solutions. And for example, with such a solution, we could take hydrochloric acid, which is often used specifically in the form of a solution. Chemical equations can be written using symbols as well as the aggregate state of the substances reacting and being formed. They represent reactions, showing the substances involved in a concise manner. Let's provide an example. Let's assume there is an interaction between solid potassium and solid potassium, for instance. This reaction will take place when water is present. In this specific case, water acts as a vital element in the process. Liquid. What will be the outcome of this reaction? We will obtain a potassium hydroxide solution. The formula for potassium hydroxide is KOH, but since it is a water solution and we are prompted, we place these letters in parentheses and also highlight the second one, which is hydrogen gas. And then we demonstrate that it is gas. However, we must not overlook the fact that every equation must be balanced, so we will need to balance this equation as well. Let's recall that we are working with the element whose index is greater. This element will be hydrogen. We've got hydrogen on the left side, it's an even number 2. On the right side, it's 3, an odd number. Then we put a coefficient of 2 in front of the formula. Now we have 2 hydrogens on the left and 4 hydrogens on the right. So before the water formula, let's put a coefficient of 2 so that there will be 4 hydrogens. We will also see the testoroda, that it is 2 on the left and 2 on the right, and potassium is 1 on the left, 2 on the right. So let's put a coefficient of 2 in front of the potassium formula. So the equation looks like this. 2 potassium solid plus 2 H2O, that's liquid, equals 2 potassium OH, aqueous solution, plus H2, that's gas. This here is a good old-fashioned substitution reaction. Alright, on to the next example. Let us consider, for instance, aluminum oxide as an example. So we're signing the first letter of this name, meaning it's solid. And he reacts with a concentrated solution of hydrochloric acid. This is H-chlor. So what's the reaction result? You'll have a solution of aluminum chloride. And because it is a water-based solution, we also ensure that we label it as a water-based solution. And the second product of the reaction will be water. Water naturally comes out in the form of a liquid. Now we need to equalize. Just a reminder, this is a reciprocal reaction. Can you also exhibit an additional minuscule frame to make it easier to align the equation? Okay, on the left we have 2 aluminum and on the right we have 1. We place aluminum chloride 3 in front, coefficient 2. Chlorine on the left side is 1 and on the right side it is 6. So we place a coefficient of 6 in front of the HCl formula. On the left side we have 6 hydrogens and on the right side we have 2 hydrogens, so we set the coefficient for water to 3. And we verify the presence of oxygen on the left side of oxygen element 3 and on the right side of element 3. This is a reaction known as swap or double replacement. An additional example will be presented next. Let us consider ethylene in its gaseous form. Ethylene is an organic substance that exists as a gas in its natural state. We're discussing the burning reaction. The burning reaction happens in the presence of oxygen. Oxygen is additionally a gas. Throughout the course of this reaction, carbon dioxide is produced as a byproduct. However, carbon dioxide is also in a gaseous state, which is why we assign it the same symbol. The second product of the reaction will be water. In this case, water will be released and may undergo condensation to form liquid water droplets. Reminder, when balancing an equation, we start by equating the carbon atoms in the first element. 2 carbons on the left side, 1 carbon on the right side. Put a coefficient of 2 in front of the CO2 formula. There are 4 hydrogens on the left side and 2 hydrogens on the right side. So we add a coefficient of 2 to the water formula. And oxygen in such cases is equated to the last ones. On the left side there are 2 oxygens and on the right side there are 4. 2 multiplied by 2 and an additional 2. In total there are a combined 6. Therefore we assign a coefficient of 3 to the oxygen formula. C2H4O2 equals sign 2CO2 plus 2H2O, a liquid. Adding 302 gas gives 2CO2 gas and 2H2O in liquid form. Another example. Let us consider a solid substance, zinc. Zinc is a metallic element that undergoes a chemical reaction with diluted sulfuric acid. The chemical formula of sulfuric acid is H2SO4. This substance is a solution that contains water. In the substitution reaction, zinc displaces hydrogen, converting zinc sulfate, ZnSO4, into an aqueous solution. Simultaneously, hydrogen gas is liberated as a byproduct of the reaction. Hydrogen demonstrates that it is a gas. Subsequently, we need to verify if equalization is required for proper functioning. Alright, we can go here from left to right. We can check the oxygen. If its index is greater, it's inequality. Gray naturally is also included. Hydrogen 2 is present. Zinc is added 1 by 1 sequentially. Our equation does not require any additional coefficients, which means that all the coefficients in this reaction equation are equal to 1. And let's give another example of a reaction. Let it be a decomposition reaction. As an illustration, a water solution of hydrogen peroxide, and this substance is in a liquid state, undergoes decomposition under the influence of temperature, and hydrogen peroxide can also decompose under the influence of certain catalysts, resulting in the formation of H2O, and water in this specific case remains in a liquid state while oxygen gas is released. This is a breakdown reaction. Alright, let's start leveling the playing field. From which item? We initiate with O2 since its index on the right side is the highest in the overall sum of elements in the system. On the left of him there are 2, on the right of him there are 3. Here it is even, here it is odd. Let us utilize the rule. Where it is odd, we will make it even. Therefore, let us place 2 here. Now there are a total of 4 oxygens, and on the left side there are 2. So let's put a coefficient of 2 in front of the hydrogen peroxide formula here. And let's double check the hydrogen as well. There are 4 hydrogen atoms on the left side and 4 on the right side. Our decomposition equation is set equal. Let's read it. 2H2O2 liquid. It breaks down under the influence of temperature into 2H2O liquid and oxygen in the form of gas. So today we once again practiced with you the skill of composing chemical equations. This is a strategy of immersing oneself in chemical equations. And today we included, I hope it is clear how it happens, we included additional aggregate states. And hopefully, for substances that you will encounter quite frequently, such as oxygen, water, some acids, solid substances, and metals, you will also remember their states of matter. For you, indicating them behind substance formulas won't be an issue as shown in these examples. Here we are again, figuring out coefficients in reaction equations together. Hope that's clear too. That's all for today. Goodbye.